So the twin paradox is something that's always kind of bugged me since I was a kid, and I've seen a few videos on YouTube that claims to explain the twin paradox, and they all felt wrong to me, and they're all very confusing. And I saw a diadetic's video, which explains how those videos are all actually incorrect. So I took some thinking, and I've actually figured out the twin paradox. This is not clickbait. I've actually figured it out. And this solution is actually really, really simple. And there's no fancy math, or fancy physics, or fancy time graphs. It's pure logic deductions. And I made the things deliberately complicated just to show how simple the answer is. So we have quintuplets, so 5 twins, or quintuplets. So we have A, who's on Earth, B, who is moving to point B. Imagine that as a space station, and for 2 light years and then coming back. We have D, who's doing the same thing, but perpendicular. So 2 light years this direction. We have E going in a circle, and we have C that's going to the left. I know a lot of solutions of twin paradox may talk about acceleration or fiddling force or whatever, and I'm going to say that's not true at all. And in fact, for the sake of for our example, we'll just say there's no acceleration involved. In addition, there's no gravity. Don't worry about that. Again, this is pure deduction. So with regards to our example, with the 5 ships, when we come down, we can actually, we can calculate time dilation through mathematics, and we calculate that there's some time dilation involved. For most notably for B, they've only gone through 6.9 years have passed when they come back, whereas A, 8 years have passed. But again, we have the twin paradox, in which case, why can't we say that B is the one that's moving? So first, I'm just going to quickly explain what the twin paradox is. So we have A and B. So let's just say this. So B is traveling away and coming back. So when we do time dilation, we calculate that B has traveled, less time has passed for B than A. And the question with doing a twin paradox is like, how can you say that B is the one that's traveling, and why can't we say that B is stationary and A is traveling by that definition? Shouldn't A have age less than B? Oh, my solution's kind of like very simple. So why don't we just take a look at B's perspective? So to A's perspective, B is moving away 2 light years away, and then coming back. So let's suppose this. Let's get into the spaceship with B. So we're in the spaceship with B, and what would we see from here? So what we see is that we would see that A starts moving away from us at 0.5 c, while B, or point B, the space station, moves towards us at 0.5 c. Okay, and once we reach a point, once point B hits us, when he hits us because he's traveling towards us, point B will then move away, and while A, or Earth, will move towards us. So that's what we see in point from B's perspective. So I propose a very simple question for you. How far away is point B towards us when he starts moving? Or a better question is, how far away is A and point B, the space station? And again, the very simple answer would be 2 light years. Or is it 2 light years? Think about that for a second. Okay, so just a short rundown of what length contraction is. So when an object is moving really, really fast, the length actually shrinks, so it gets shorter, hence length contraction. So this train here, let's suppose it's going fast, it actually gets shorter. Here's the thing. What if we are on the train itself? Obviously, we don't get shorter. Because we're on the train, we see that the entire track is moving to the opposite direction. So length contraction would mean the entire railroad track gets shorter. So let's get back here. So what would we see when we're in B's spaceship? Well, a very simple question would be, well, how would length contraction work in this case? Now, between A and point B is obviously not completely empty. There could be asteroid, there could be objects, there could be other things, and all of these things would get contracted in length because, again, B is moving. Or in this case, the entire, A and point B are moving. But let's think about that for a second. What about the actual space between A and point B? Can space, which is absolutely nothingness, contract in length? Or can the universe contract in length? And the answer is yes. So the entire distance of A and point B would become shorter towards B's perspective. This is kind of confusing. How can nothingness contract in length? Well, that's how length contraction works. So one major mistake with the twin paradox is the assumption that A is a separate entity to whatever destination that B is traveling to, and it's not. So instead of thinking as A as just this own thing in the middle of nowhere, think of A and B, point B, as almost a single entity. Almost imagine there's like a railroad track or a line that goes between A and point B. And when B is moving, or A and point B is moving. In fact, yeah, sure, why don't you imagine there's a giant tether between A and point B, and that's kind of makes it more simpler towards us. So what we see, again, we're stationary, right? So we see this A and point B sort of super tether is traveling 0.5 c to this direction. That's what we see, and what we see as the length of that tether. Well, so if we think about that for a second, there is no actual symmetry. A and B do not agree on the same observations. A sees B traveling away for 2 light years, but B only sees A traveling away for 1.7 light years. Now, intuitively, if A sees B travel for 2 light years at half the speed of light, obviously 4 years would have passed. But if B sees A travel away at 1.7 light years, then obviously only 3.4 light years would have passed. That's very intuitive. In other words, the solution to the twin paradox is that there is no twin paradox. The two observers, A and B, do not agree on the same thing, even if they are both stationary. Because A sees B travel for 2 light years, whereas B only sees A travel for 1.7 light years. In fact, the math totally adds up. Again, there is no twin paradox, because there is no symmetry. If we go back to our original example, assuming B, D, and E all travel for 4 light years, again, it doesn't matter the shape. They could be going in a triangle or a cyclone or something weird shape. They would be traveling at half the speed of light for the same distance. They would all come back the same age due to time dilation. And again, it's actually simpler to, instead of thinking about as time dilation, think of it as length contraction. Don't think about the time, the clock's slowing down. Think about how much distance the other person has actually traveled. That's the best way of interpreting this. Naturally, if a person or a ship or a planet travels for less distance, like in 1.7 light years here, it is natural that less time would have passed with regards to whatever observer. Yes, I think it's quite confusing to think that the entire universe will contract in length, but that's how length contraction works. So let's have like a thought experiment here of what would happen if the Earth is moving. So let's say the solar system is traveling at half the speed of light towards some point. Well, if that happens, then to our perspective on Earth, the entire universe from that direction or that orthogonal would actually contract, become shorter. It's again quite confusing to think the entire universe would be shorter, but that's how it works. That's how length contraction, time dilation works. In fact, if we take a look at E's path of going in a circle, because E's direction is constantly changing, the contraction length would actually change. So it would have this weird sort of effect, in which case, whatever that particular angle, that would contract in that direction. In fact, this orbit of the circular path would actually appear to be an ellipse to point E, to ship E, except E would always be on the edge of that ellipse, never in the center of it, because E would always be on the shorter side of that ellipse. Yes, that's how length contraction works. Don't think of it as time dilation, think of it as length contraction, how much distance something has traveled. Now, one common question would be like, does it make a difference if B travels to and comes back? Because one simple assumption is that, you have to actually, B has to travel back to Earth A for them to match their clocks to see who's older and younger. And the answer is no. It doesn't matter if B goes on and travels forever. It doesn't matter if B just stays at point B and never comes back, or B never ever stops traveling. All that matters is how much distance has traveled. If A thinks B has traveled for, 200 light years, well, B interprets only, 170 light years have passed. Naturally, a different amount of time would have passed with regards to different time dilation. So again, you don't need to the twins don't actually need to meet again for the sake of the twin paradox. Again, it's not a twin paradox because there's no actual paradox. Okay, so some of you might still be confused or, in disbelief that this is a solution to a twin paradox. So I will explain it further with this bonus section. So we have ship B and ship D traveling away from each other at 0.5 c, hitting point B and point D respectively, and then coming back. Again, they travel for 2 light years each before turning around. Now, we've already done the time dilation calculation earlier. We see that while A has passed 8 years, B and D have both experienced 6.9 years. They actually experienced the exact same amount of time dilation. The exact same amount of time has passed. But again, we go back to twin paradox, which is, suppose B thinks that they're stationary, and when they see D leaving and then coming back, as such, D should experience time dilation. D's clock should slow down. But D would see B as being moving away, and D is stationary. Okay, so let's look at B's perspective. So we're going to be in the ship with B and pretend that we're stationary. What exactly will we see? Okay, well, we would see PB and PD, the space stations, moving towards the left at half the speed of light. And we would also see D moving away from us towards PD at a certain speed. Now, what is the speed that D would be moving? Again, we are stationary. We're assuming that we're stationary. Well, if we look at from A's perspective, A would think that B and D are both moving away at half the speed of light. So does that mean B sees D moving away at the speed of light if we add them up? Well, actually it doesn't. So because of the speeds that B and D are moving at, which is at half the speed of light, you would actually have to do an Einstein velocity addition to find out what their actual relative velocities are. So B would actually see D as moving away at 0.8 c rather than at the speed of light. Okay, and of course we need to figure out the distances that B would see D traveling. And it's actually pretty straightforward. We already knew earlier that the distance between Earth and point B is 1.7 light years. Again, from B's perspective, given length contraction. So the length between PB and PD would be 3.5 light years, or 3.4 light years, from B's perspective. Again, from Earth's perspective, there's a distance of 4 light years, but from B's perspective, the distance is only 3.4 light years. Now, remember earlier, B and A, or Earth, do not have symmetry. They do not agree on the distance traveled. But in this case, B and D do agree. They see the exact same thing. And when they get back to Earth and meet up with each other again, the exact same amount of time dilation has occurred. 6.9 years would have passed for B and D, but Earth, 8 years have passed for Earth. So now we take a look at D's perspective. What does D see? Well, D sees the exact same thing B does. D sees PB and PD are moving to the right at half the speed of light, and D sees B is traveling at 0.8 c for a distance of 3.5 light years. Again, D and B see the exact same thing. They agree. They have symmetry. So again, because B and D have symmetry, the same amount of time would have passed for both of them since they've traveled the same distance. And they can agree on the distance that the other one has traveled. Which, again, assuming each of them are stationary, would be 3.45 light years at 0.8 c. Now, again, it doesn't matter if the two ships are moving in perpendicular, or they're moving against each other, or someone's moving in a triangle, or some weird shape. All that matters is what is the distance traveled. So, because B has traveled less distance than A thinks B has traveled, B experiences time dilation. But B and D have traveled the same distance at the same speed. So when they come to see each other again, the same amount of time would have passed for both of them. And they would experience different amount of time dilation than A does. And again, it doesn't matter if it's parallel or perpendicular, because again, what matters is distance. If they're perpendicular, yes, the relative velocity would change at a different angle, but they would still have symmetry. So B would see D as moving at some weird angle, but D would see B is also relative, moving at a different angle. Again, they have symmetry. When they have symmetry, their times would have to agree, because they see the exact same thing, but in the opposite direction. A and B do not have symmetry. They do not agree on the distance traveled. So naturally, different amount of time would have passed for them. So it's important to remember that time dilation and length contraction go hand in hand. You cannot have one without the other. Whereas A would see B, the ship itself, shorten as it's traveling, B would see the entire universe shorten as B is traveling. So to put it in perspective, you can actually say that there's a universal kind of constant of stopping, but not really, because you're right. The entire solar system of Earth could be traveling at a certain direction. We don't know that. All that does is that would create a length contraction in that direction from respective to the universe or some other object. But from A, B, C, and D, and E, the amount of length contraction they experience would determine the amount of time dilation they experience. And again, we see this with satellites. The satellites are orbiting the Earth. They're moving at such high speeds that they experience time dilation. But do not forget, the same satellites that are orbiting the Earth are also experiencing length contraction. So the orbit that they're taking around the Earth is actually shorter than what we think is their orbit. Okay, so that's the twin paradox, and as you can see, I didn't use any fancy math or like fancy time graphs or anything that's complicated. All we do is very, very simple deductions here. So if you guys think I'm right, then please share the video, let people know. If you disagree with me, please leave a comment and argue against me. I'm happy to take criticisms. But anyways, thanks for watching, and if you like the video, please share it.